Last week on Tuesday, we talked about the uniform convergence. I want to remind you what were the important points we discussed. So first of all, let Fn be a sequence of functions in some segment I. We say that Fn is uniformly convergent to some f. We denote it with Fn right arrow to f. Yeah, that again. What do you want? It's right arrow, right? It was right there. No? Am I missing something? Right arrows? Ah, okay. If for every positive epsilon, there is some n epsilon such that for every n, for all, whatever, n greater than n epsilon, and for every x in the segment, we have that the distance between f and x and fx is smaller than epsilon.
You remember what we said I was?
Segment. I don't use a psic b or something because it can be in an infinite segment, like even all of the real numbers.
Or interval.
Yeah, an interval. So this is the with the letter I. We use what? What did we say about this uniform convergence? We said two things. I want to add a third one and then prove what we haven't proved yet. We said that theorems or something like that. First of all, Fn is uniformly converged. It's the sequence. It's uniformly convergent to f if and only if Vn tends to 0 when or where Vn is the sup of all segment, all x and I, of the Fnx, environment, Fnx minus Fx. We've already proved this number one theorem on Tuesday. Secondly, we said it, but we didn't prove it, that if Fn is uniformly convergent to F and Fn are all continuous, then thoroughly F must be continuous as well.
Yeah, and we said it's not bidirectional, right?
No, if F is continuous, it doesn't say anything about Fn. What we did say, the equivalent phrasing of this sentence is that if Fn are all continuous and F is not, then Fn are not uniformly convergent to F. It's one way to disprove uniform convergence, but it's not mentioned if and only if. I mean, Fn can be continuous and F continuous as well, and yet the convergence is not a uniform one. We had our examples last week. All the functions were continuous, but it wasn't a uniformly convergent sequence of functions. So we said that, but we didn't prove it. and I want to add something else. If Fn goes to F and Fn are all integrable, then F is in I, segment we talk about. Then F is integrable in I. Moreover, the sequence of the antiderivatives, as we saw on lecture number 6, which is the integral from some a to x, goes to, and that's not it goes uniformly to the integral of f itself. Last Sunday, we gave a counterexample when the convergence was only pointwise. The integrals of Fn did not converge to the integral of f. Here I claim that the integral of Fn as a series of functions of antiderivatives not only converges to the integral of f, the antiderivative of f, it converges uniformly. So what I want to do now is prove 2 and 3. As I said, we've already proved number 1 in lecture number 13. Before we do it, any questions? The font is big enough? Is you big enough? Okay. So, proof. One. Yeah, so one way we've already proved it. Lecture number 13. It's fun. Extraordinarily fun. Yeah. 2. Okay. We know that Fn goes to F and Fn are all continuous. I want to prove that F is continuous. Continuity is how do we say it in English? It's not pointwise. We've already used this word, but what I want to say it's not. It's a property that happen or not for every point. So if we want to prove that f is continuous, we take some general point in our segment in our interval, and we prove that f is continuous there, meaning that let I don't know xf is some point in I semicolon. We want to show that the limit where x goes to xfs of fx is fxfs, x0. This is the definition of continuity. The limit at a point and the value at this point are equal. So, what do...
Is there a possibility where we have a function where the value is a defined value, but the limit doesn't equal the value?
Yes. Called the Hebrew slang a whole point. Yeah. Something like that.
Right, yeah.
Yeah, because the point is something else and the point could continue. Like sinus x above x or something. That the limit does exist, but the value on the point is something else. Okay, so what the limit of x go to xf as fx is xfx. By definition, I like to use the Heine definition using sequences in order to prove something about limit of functions. As far as I know, Erez, that's how we like to do it as well. So probably that's what he did, at least most of the in Q1, which is very fun. By definition, where's my cursor? Okay. Let xn, the same index We want to let's find let xm, don't know, for a different index than n, let xm I be a sequence such that xm goes to xfs, and we need to show that fxm as a sequence of numbers converges to the number fxfs. Because we do it for every sequence, we prove that the limit of the function is fxf, fx0. Okay, so that's what we want to show. What do we know? Yeah, let's take it another step forward. Still, don't prove anything. Just say more precisely what do we actually want to prove. I want to use epsilon, etc., because that's how the definition of uniform convergence works. So let var epsilon be greater than 0. We need to show that there is an epsilon such that for every no m, because this is the index that shows now, larger than epsilon, we have that fxm minus fxfs is smaller than epsilon. This is by definition the convergence of a sequence. Here the sequence is fxm and the limit is fx0. So I want to prove that. Now,
we wouldn't know that the convergence.
no, I want to show that what do we do know is that fn goes to f pointwise. For every point, fn of x goes to fx about the HFN. And we know that fn are all continuous. And moreover, we know that the convergence it's not just a pointwise convergence, it is a uniform one. So how do we use all this in order to get what do we want? What do we know? Yeah?
Three.
No, two.
Unfortunately,
What?
well, I just asked. I just what? Did I not just ask whether?
Yeah, I know. So you're saying we know that if n converges to f
Yes.
uniformly, and that if n are all continuous,
Right.
we have to prove that the convergent function is continuous.
Yes, the depth is continuous.
Okay.
So again, continuity is by definition that one. The one to prove of fx when x tends to xf has to be fxf. The limit and the value are the same.
I get that, but when we said let the whole epsilon, let epsilon be above zero, and then we need to show that there exists an epsilon.
So, but by
Why
the
we need to do that? Because we already know that it's uniform when we convert.
no, but the uniform convergence is talks about fn and f, not f itself. I want to do something about f. The difference between fxm and fx0 is going to 0, is smaller than epsilon. There is such an epsilon such that.
Okay.
So what do we know using the convergence of the sequence fn and so on? We know that fn right arrows to f. So there is, let's call it n1 such that for every n greater than n1 and for every x and I, we have that fnx minus fx is smaller than our epsilon. And moreover, let's, it's the same epsilon, but I want in the end to get a subtotal of epsilon, right? So probably I take your epsilon above 2 or above 3 or something like that, as we used to do mainly from the first course. Moreover, or furthermore, why not? Furthermore, Fn are all continuous. So when it comes to Fn, the sequence of the numbers Fn xm goes to Fn of xfs. You can write this about Fn for every n, meaning that there is, I don't know, n2, such that for every m greater than n2, we have Fn of xn minus Fn of x0 is smaller than epsilon. No. So we know this for every x1, right? And we know that. And we want to get from here to there. I mean, we can write these specifically. We can say
But the definition of uniform convergence, can we say that there exists another x being x1 where for all the limit of x going to x1 means that fn x1 goes to fx1 like that, or
yes, that's what I want to say here. Know it for every x in I, so we can specifically set it about, first of all, the numbers of the sequence. What? And secondly, you can say that about the point itself, x0. So now I can use these three expressions, which I know all of them are smaller than epsilon, in order to prove that this expression is smaller than epsilon as well. And then, as I said, I need to take here, and I can do it because I know it's true. I know that it will be true, whatever expression of epsilon I'm going to put on the right hand of the inequality. So we used to do it here, half epsilon, and together epsilon. It's not the first time you do it. As far as I can remember, we've already done something like that on Tuesday, proving about the dn or something. We used half epsilon, then got to epsilon or something like that. So if we look, this is some n2 that it goes for it, and this is some n1 it goes for that. So let's have n epsilon to be the maximum between these levels of the sequence, n1 and n2 indexes. So after an epsilon, all of our equations, inequalities, um, occur, and we can say that triangle inequality help us to get what we need. For an epsilon maximal, we have,
Sorry, Eva.
yeah,
Can we state it like this without like saying different x10 and different x3 or like it, we don't need to like say different variables for each and then say that we can just find the maximum and that's right, like can we just say it like this?
no, from this maximum, from this level and so on, I know that all my inequalities do happen. Now, the equality we want to achieve connects between the f of xm and the f of x0. We have to, in order to use what is given to us, we have to take 3 steps. We know to talk about fn when it comes to the xm and x0. And we want to talk about fn and f about the same point. We want to talk about f when it takes m and x0. And again, we know about fn about xm and x0 and fn and f at the same point. So we have to take these 3 steps in order to get what we want. If n is greater than n epsilon, we get the following. One of the oldest sticks in the book. If you want something, you add it and you subtract it. So we can talk about fxm minus fnxm plus fnxm and minus fnxfs plus fnxfs plus whatever. And here we have the 3 expressions we know about just in one big warm absolute value, and I can not equal, it's less or equal by triangular inequality. We can break it up to 3 different absolute values, and here for every absolute value we can talk about, okay, it is smaller than the third of epsilon, each because of its own reason. Fn xm minus Fn xfs, we talked about Fn without F, is because Fn are continuous, and Fxm and Fn xm and Fnxf at 0 and Fx0 is because of the uniform convergence. Let's say it's, yes, it's true for every x in our segment, specifically for xm and xx. So each one of them is smaller than the third of epsilon, and in conclusion, we get, oh, how surprisingly, epsilon as needed. Required. That's easy to read afterwards. So technically speaking, we want to prove this. I know to go around it, yeah, talking about Fn and F, but at the same point, xm or xfs. And we know about Fn at different points. How do we use these 2, practically 3 things, in order to talk about F at different points, at xm and x0? So this is our proof. Okay, any questions? Now, about the third part of the theorem, it has 2 parts itself. First of all, I claim that if Fn are integrable, all the sums go, Riemann sums goes to whatever they need, then F is integral as well. I don't want to prove it. Leave it for the reader. All the books used to say. I don't know if you ever read mathematical texts, even for undergrads. But for graduate, no, it's the advanced text in mathematics. It's always a theorem, something extraordinarily difficult to understand. And then the proof is basic, the proof is trivial. I asked a 3-year-old and he told me the proof, something like that. They do write it sometimes as a joke in the books. So f integrable, I'm not going to prove it here. I want to get dirty with Riemann sums. We've already moved on. But I do want to prove this, that the sequences of Fn and F, the sequence of F and the integrals of Fn does converges, and moreover, uniformly to the integral of F. So, we want to show that the integral that's right. We call it, let's call it, I don't know, big D as the integral of letter we call it big. Big D n is the sum of the absolute value of the difference between integrals for every x in ith. We want to show that dn, big Dn goes to 0, where dn is this by our first theorem already proved last week. We know that it is equivalent to saying that the sequence is uniformly convergent. Okay, so I want to talk about the supremum of these integrals, and I want to write it down. The integral of no. The difference between integrals, we know we can write it as the integral of the difference between the functions. You know what? Let's write it down with the absolute value as well. I mean, why not? That's Fn F. Is the correct. That's the linearity of integrals. Now, moreover, we've already talked about it now since lecture number 5. We're at 14 now. We've already been at bar mitzvah last week. We know that the absolute value of the integral is less or equal the integral of the absolute value. Yeah, I could say that it is smaller or equal integral of a to x fn. No, something's wrong about the notation, not about the proof. We already know that if I use the letter x to denote one of the limits of the integral boundaries, I cannot use it inside the integral. So what we did, and we had to deal with this problem, we used t, t, instead of x. So correcting it here and there, should be t and t and t.
Why is that the case?
Why? We need to use different letters? Because each one of them talks about something different. One is what we put in the derivative after I find it, and the second one is the variable of the function itself. So the absolute value of f and t minus ft dt. Okay. Now we know that dn is the supremum. It's the smallest upper bound. If this expression, the integral of the absolute value, is an upper bound, which it is, then it is as well small greater or equal than dn itself. Because when Bn is the smallest upper bound, and we did get here that this integral is an upper bound, we can say that Bn is smaller than the integral. And on the other hand, we've already mentioned it last Tuesday, Dn is always non-negative sum of some absolute value, so it is always greater or equal 0. So by sandwich theorem, what's left to us is to prove that this integral goes to 0. By sandwich, so sandwich is enough to show that the integral goes to 0 when n goes to infinity. Then we'll go to infinity, to 0 as well. We know that Fn goes to f uniformly. So the difference between the integral, we know it goes to 0, but let's write it in the right way to prove what we need to do. So indeed, we know that Fn goes to f uniformly, meaning Dn goes to 0, where Vn, as usual, is the supremum of the difference between Fn and f. Now, instead of x, we can use t if you like. I mean, I had some joke about, British people, they always prefer to use t, but I didn't get it through, I'm better in Hebrew than English. It's a soup of fxn. I want to say, when can you use it, the letter t instead of x? More fitting here. Dn is super of f, and because it's a supremum, it is yet again an upper bound, the smallest one, but an upper bound. So semicolon, moreover, Dn as a soup is greater than Fn t units of t for every t. So our big Dn, which is smaller or equal, the integral from a to x of f and t minus ft in absolute value is less or equal the integral of just Dn, because it's an upper bound. Now Dn is, according to t, looking from the t point of view, is a constant. For every n, we have a different dn. Yeah, probably. But talking about t, talking about the variable of the function, dn is a constant, as we already seen such examples last week. We had the function xn, x2n, something like that, where the dn were all quarter. Well, dn is 1 above n. 1 above n is not a constant talking about the sequence, but it is a constant from the function point of view, from the integral point of view. So I can plug it out. And moreover, you know what? We know, first of all, we know how to calculate the antiderivative of a constant, just dn multiplied by t, and then we say t is x minus t is a, etc., etc. But one of the few things, yes, not many. The few things we proved in lecture number 4 using the very definition of integrability of the Riemann sum, etc., is the integral of a constant. It's the constant multiplied by the difference between the boundaries of the integral. So it's dn multiplied by x minus a. Now, when n goes to infinity, we know that, let's do it with a subset. No subset. I'll call it underset. We know that when n goes to infinity, dn goes to 0, multiplied by x minus a, which is 0. As we needed dn to goes to, the big dn goes to 0 as well.
Is the n a function of theta?
Is the integral of d.
No. What?
Integral of d now. Like you say you put a big d because it's integration.
Yes, talking about the antiderivative. Yeah. Let's write down as required. We've already mentioned last week that from understanding something about the derivatives, knowing something about the function themselves, we don't have something good to say about it, but we've stated some theorem talking about if we know something about the derivatives, then we can say it about the function themselves. Some way of hindsight, but it's not very important to mention here right now specifically. I want to move on to the subject of series of functions, and then we can state it again, but using the language of series instead of sequences. Before we move on, before we march forward, any questions? Okay.
No, I was going to
Mm-hmm.
the integral of dn.
Yeah.
That is dn x minus a.
Yes, because according to T, dn is a constant. So then you have a constant, it's just the constant multiplied by the difference between the bounds of the integral.
Right.
Or one can think of it as, okay, it's a constant. Let's say, I know, 5 or something like that in head. I always use 5 when it comes to examples of constants. I don't know why. Myself, when I think about it. And I say, okay, what is the derivative of 5? It's 5 multiplied by x, or by t right now. So 5t, put x, put a, 5x minus 5a. That way it goes to 0. It's required. Any other questions? Okay. So, we march forward to series. You told me that it's a word without a plural, right? It's a series. For tour and touring, series. Okay. Series of series. This is maybe it's like cactus. It's cacti or something weird. Series. Series of functions. Just like series of numbers. We use the sequence, the concept of a sequence in order to define series. Now, let fn sequence of functions in some interval I. We denote the series of the function. We start from 0 or 1 or whatever is given to us in a given exercise. Mathematically, it doesn't change my theorems, etc., etc. Fn x. I usually denote it with sx, something like that, as like in sum or schum in Hebrew. We've already have an example from the first infi. For example, let fn x be the functions x to the power of n in the segment -1 to 1 without -1 and 1. We know that the series of xn, where we start from 0, converges to 1 above 1 minus x. It's called a geometric series, right? And here, we can say that this function Sx is the function 1 above 1 minus x. So we already know, familiar with the case, with the example of series of functions. We probably didn't think of x to the power of n as a function in phi1, but because we studied before, we studied functions, but of course, we can do it pretty easily. By definition, let's talk a bit more formally. Formally, we denote with Sn. Let's use the big N because we already taken the small n for the index of the sum itself. Sn is called, or are called, there are many of them, for every n, are called partial sums. סכומים חלקיים, partial sums, probably that's how Eris called it as well in Infi 1. And we define Sx, which is the series, the infinite summation of Fn to be the limit of Sn when big N goes to infinity. Where's my cursor? Where are you? Yeah. Meaning that if the sequence Sn converges, then we call the limit Sx, and if it is divergent, we can say that the series or that Sx is divergent when or if the sequence here, the sequence of Sn converges, we say that the series converges and the limit is Sx, as in the 1 above 1 minus x, as in the geometric series. And vice versa. I mean, if Sn diverges, we say that the series is divergent or diverges. You prefer the verb instead of the adjective. But here we can add and say similarly, if the sequence Sn uniformly converges to this function f, then we say that series infinite summation uniformly converges and to S again. And let's write it further so we can note that first of all Sn, right arrows. S or the sequence, the series itself goes to S. I mean, It's a bit, it really happened in if you want as well. So it's not complicated, but it's a bit tricky notations. I mean, the series equals S. It means that we can call it the sum of the series, something like that, but it's the series itself. I mean, the series, when it comes to numbers, it is a number if it is um, convergent. And here it's a function, because series is a function. But on the other hand, we don't say that a number converges, or we don't say that a function converges. We say that a sequence converges, right? So we think of the series as a limit of sequence, the sequence of partial sums. So when you think about it as a limit of sequence, we say, okay, the sequence converges. But instead of saying the sequence converges, we say the series converges, which is totally fine. We can say whatever we want to say as long as we agree about the meaning of what we're saying. But if you think about it, saying the series converges is a bit weird because the series is just a number or just a function when it comes to series of functions. But we've already talked that way in Infi 1, and we're going to do the same here in Infi number 2. Infi can 2, twice the fun or something like that. So the definition is practically the same. We just add this little x as definable of the function, but partial sum and the limit and whatever it needs be. We're going to mention, not today, maybe not this week, but later on, and not so very later, all the more of the comparison tests and all the tests of conversions. I will mention the last later on. Next week we do not study on Sunday. It's Hanukkah Chofesh, freedom, holiday, whatever. Yeah, it's right word. And the week after that, in 2 weeks, we don't study on Tuesday. It's Asara B'Tevet.
Sure.
Asara B'Tevet. Yeah, so we good. We're good when it comes to, to according to the syllabus and do what we are planning to do. Don't we have to do some
Or the class teacher
like what?
does not needed to do a makeup lesson.
No, we don't need to rush things up on one hand, and on the same hand, we don't have to have another lessons right now. Basically, I always plan on 26 lectures, meaning full 13 weeks. Now, as far as I know, we have 14 weeks in the semester, but we've already lost one lecture for the opening ceremony or whatever, and we're going to lose one lecture of Hanukkah, one lecture of Sardevet, which leaves us with 25 lectures and not 26. But for one lecture, I'm not going to work harder, let's say that way.
Because we lost one for the opening of the year.
Yes, so it's a total of 3 lectures missing. So instead of the planned 26, we're going to have 25. And this Tuesday, we miss half an hour. We finished 13 because of Hanukkah. We will manage, okay? Without any additional lessons, without nachs, that's in Hebrew. But if I knew, at the beginning, I had semesters like lectures that, happens afternoon or in evening, you miss sometimes 3 lectures just on Hanukkah. I had, it was in F1 a couple of years ago. I missed 3 lectures on Hanukkah, one on Asara B'Tevet, and there was some elections, but not for the state, for the municipality, something like that. It was already another holiday. So I started with 23 instead of 28. Maybe I'm sick, they're sick, I don't know. So I told them from the beginning of the semester, listen, we're going to have, yeah, always time. Love sick for Infi. We told them, listen, we have to do at least 2 additional lessons outside the schedule. But here, 25, just doing the most important, not important, but it is important. It's the same for the Hebrew class. We do the same pace, going at the same pace according to syllabus, and they do miss a lecture on Sunday and on next Tuesday, so you don't need to rush. You don't have to have an additional lesson. If no, we're going to be sick, hopefully not, and then we'll see what we can do. I'll tell you that it's the Infi 2. If it was Infi 1, it's to rush it to get to Infi 2. Infi 2 don't have Infi 3, right? Bismillah. Don't have Infi 3, sometimes to rush it as well.
I think that like the most important thing we can learn related to this is Fourier, right?
Is what?
Fourier.
No, you're not engineers. Bless. So you don't have, yeah. Baruch atah, don't make you engineer.
Yeah.
But no, the important thing is Taylor. Don't know if you've already. Aaron's probably so. He likes to. No, he didn't mention it. Taylor series. Yes.
Our lecturer for probability expected us to already know Taylor series. Like, huh?
Probability is an important course for the current situation of computer science, which is AI. It is an important course. So here, I don't say it in the people say the kodkodim, which is it's a slang from the army, or the leaders of the department. Yeah. Surprisingly, they listened to reality, and they no, because university sometimes they off grid when it comes to what actually happens outside the gates of the university, and they do whatever they want. And we are an honorable institution. You have to do whatever you want, and then you go out to find a job. It's your problem. No, they listened, and they used to teach the probability course in your third semester. Which in semester A, yeah, you would start in spring, it's something else, but semester A, semester B, and only semester C. And they said, you know what, it's too important to leave it to semester C. We need to teach them courses about AI in semester C and D and B and F. So you want them to study probability in semester B already. But probability needs some of the mathematics taught in Infi 2 or linear algebra 2, and we cannot squeeze it enough to one semester. So in the last 3 or 4 years, it do happen. You study probability this semester or only?
Yeah, we're studying this semester, but
so we probably show you some of the properties of functions with more than one variable before we saw it here. Before we will see it here. I don't know the exact tense in English to say what I want. But the price it's small in order to finish probability in your first full year as computer science students. So back to what you say. Fourier, engineering, French, not good, not good. We, Taylor, computer science, British, very good.
Yeah.
Okay. So yeah, we are going to get there. It's 14, 15. Next we only have 16. After that, only 17. Talk about the lectures, yes. So, and only after that, 3 weeks from now, we get to lectures 18. But probably 17 already. I don't know, but we'll talk about it. It's coming soon. The Taylor series, which is it's important. I like to frame it as the most important thing here in our course, but integrals, it happens all the time, in probability as well. And yeah, the sequence of functions leads us to, right now, series of functions, which will lead us to Taylor series, which is important from my point of view. It's not the only point of view, probably not the main point of view, but it is. Okay, so in order to get to Taylor series, we have to study. Let's continue. Yeah, a little thing about studying. I want to, as I mentioned, rephrase the theorems about sequences of functions. Yeah, if it all continues, then it is continuous, etc., etc. But in the terms, in the language of series. It's not going to be very different, but we need to do it because we're going to use it all the time if we're going to study about series of functions. And the sequence of functions had 2.5 lectures, right? Last week and half of this lecture. The series is going to have have, I don't know, this, what's left of this lecture? More, 4.5, even 5. Let's roll and see. Okay. Now, so we can rephrase our theorems about sequences of functions in the terms of series. By the way, let, I don't know, let's use this notation, even without the indexes. That's because I want to use them, just because it's pretty ugly when it is in a line of language, like English or whatever. Let fn be a series function. Be a series. So we say S series, but or just series because it's plural. It's a weird word. It's a weird word. Let f be S series because series is just one, a single, or
you don't have to. Yeah, that'd be a series.
Okay. There'll be a series of functions in I. First of all, if the series is uniformly convergent, and Fn, I want to say it, no. And Fn are all continuous, then the limit function, which I call S, is continuous, and you might add as well. Sounds nice. In a different color, I want to explain something here. It's not immediate, it's almost immediate. Preferred color for my pool?
Violet.
Violet. That's the elegant purple. What I want to say, the theorem itself is something like if Sn and the sequence without this I uniformly convergent. Oh, why are you blank? Uniformly convergent to S. This is by definition saying that the series is uniformly convergent. Now, our theorem is that if all the functions in the sequence are continuous, then the limit function continues as well. So the functions in the sequence are not F, are S. I mean, it's F1, F1 plus F2, F1 plus F2 plus F3. That's how we define partial sum. Why do I say that if Fn are continuous, then S is continuous? Because if Fn are all continuous, then Sn are all continuous. Now do I know that? Because Sn is a finite sum of Fs. So a finite sum of continuous function is continuous, is a continuous function. Are continuous as well as a finite sum of continuous functions. So I can say, yeah, if Fn are continuous, without any connection to convergence, we know that Sn are continuous, because every Sn is a finite sum, blah, blah. And by our theorem, Sn uniformly convergent to S, Sn are all continuous, then S continuous as well. Now, instead of Sn uniformly convergent, I say the series is uniformly convergent. That's our first theorem. Secondly, what about the integrals? If the sum is uniformly convergent, then the sum of the integral of Sn is the integral from, let's say, a to x, something like that, of Snt, uniformly convergent, right arrows, ice, baby, to the integral of f. I know it's the same word and then another word. No, same structure, same structure. Yeah, it's all words. Just think about it. Yeah. Now, what is Sn? Sn is the sum. We can write Sn as the sum of, we know the finite sum from 0 to some n. And when it comes yet again, it's the same as in the continuity. And when it comes to a finite sum, we can put it out, the integral. And it's the linearity of integral. And we know that thing is going to goes to infinity. There is one can write. On the other hand, instead of st, we can write the series of the functions. That's what the notation says. And they are the same. The limit of Sn of the integral is the integral of S by our theorem about the integrals. So we can write down that both of them are actually the same thing. They are equal. The integral of the series of the integrals on one hand, which is the limit of Sn, is the integral of the series on the other hand. Now, it's obvious. It's one of the basic properties of integral, linearity, when it comes to a finite sum. It is never obvious to take the step from finite sum to the infinite one, to the series. Technically speaking, I call it in Hebrew, I call it integratio ivar ivar, integration element by element. I mean, calculating the integral of the series is calculating the integral of every element in the series. And then, of course, sum it. Yeah.
Why have we switched back to f of x?
Because I was wrong. Where? You're right. Same thing. Precisely. Where? No, it's fine. Without the integral, I can use x as the variable. The problem starts when you have an integral and you use as x as one of the boundaries. We call it integration. Integration I call it element by element, which probably is an more elegant way to call it in English. Element, I don't know. It's not the exact right place to do it. Probably on Tuesday it will be more fit, but let's do it as well in violet, as you already chosen. For example, we know that. Oh, for example, let's use something we know. The integral n goes to infinity from 0 to infinity of xn is 1 above 1 minus x, right? So what did they actually said here? I can perform. Who the hell is all these unknown numbers? Integration on both sides. But everyone can just write integral here and here. What our theorem states is that when you write integral on the left side of the equation of the series, you're actually integrating. Let's start from 0 because it's a nice number. The function, every function itself. From x yet again becomes t. And here you integrate the function, whatever it is, 1 above 1 minus t. This is what our theorem states about this specific example. Now we can move on, can march forward, we can calculate whatever we have here, but it's not continued. That's right. Whatever. But it's not what I wanted to show here. This is the example for our theorem. How do I integrate both sides? Integral of the Sx, the function. Okay, integral function. Everything's good. We just change t and x, but on the left side of the equation, when I integrate the series, I actually integrate every element separately and then sum all the integrals we have. Here we know how to calculate both of integrals. The integral. So let's do it. Let's roll. The integral of Tn is Tn to the power of n plus 1 divided by n plus 1. And we have to plug in x0. Choose 0 because this leaves this number to work with. And here the integral of 1 above 1 minus t is, as far as I can see, it's ln, but with minus because it's the inner derivative. T goes from 0 to x. And so when we put 0 instead of t in both sides, we just get 0. So here it is x to the power of n plus 1 above n plus 1. And here it is minus ln of 1 minus x. And this is a different sum. I mean, we see it's the first clue to what we're going to be able to do after we finish talking about series of functions. And one of the things we're going to be able to do is to calculate different sums. Not just say if they are convergent or not, but actually calculate to what number they converge. For example, if you put here x equals half, you get the sum of 1 above 2 to the power blah, blah, blah. We didn't know how to calculate such infinite sums in infi1. But we do know how to do it here in infi2. I want to note two things. Don't want to write them down, but maybe let's write them down. One of them, of course, we need to know that the series is uniformly. Uniformly. No, formally. Okay. Convergent. Um, we have our definition, but we know from Infi1 that using the very definitions of sequences when it comes to series, it can be a very big mess. I mean, every function in the sequence is now a partial sum. More and more functions are added when we look at the bigger and bigger ends, and we don't want to do it. In Infi1, don't know how Erez exactly did it, but we probably usually have one lecture about actually calculating the sum, actually using the definition as the limit of the partial sums. And then we move forward to the convergence tests. We use the comparison test to prove the limit comparison test, and we use the comparison test to prove the Lambert and the Cauchy square and root test, etc., etc. We try to not use the definition of partial sums because it is ugly. Here, we don't have to directly use the epsilon definition of uniform convergence, but if we try to use dn, we're going to see it next lecture. If we're going probably today, now let's see how we go. If we use dn, but here instead of f, we use s, it is still ugly. It is still an infinite sum inside the absolute value, not good. So we're going to talk about how we can, I'm not saying easily, but easier, showing that a series of functions is uniformly convergent. But let's leave it to lecture number 50. That's one thing I wanted to note. That's why I write it in violet. We need to know that the series is uniformly convergent. How do we prove it when it comes to series? Let's talk about series. Let's talk about it on Tuesday, Bezrat Hashem. But for example, that's for you to know. If yes, for example, if we do know that this series is uniformly convergent in, let's say, from -1, including -1, because if you put it -1 instead of x here, you get a Leibniz series, which we know that is convergent. We can put, for example, x equals -1 and get the following nice, basic, but not intuitive sum. Here for -1. On one hand, this summation gives us -1. No, you missed the equality. -1 plus half, -third plus quarter, etc. And on the other hand, it's just minus ln 2. Now, this is a basic sum from Infi1, the alternating sum of 1 above n. We didn't have, as far as I remember, the first course, we don't have the right mathematical tools to calculate it, but now it's pretty easy. You integrate the known geometric sum and you put in x equal -1. As I said, one of the things we're going to know after we finish talk about series of functions is calculating sums of infinite, sum of series, sums that we did not know how to calculate when it comes to Infi1. Yeah, question.
Why can we take away the t like the t equals x, t equals 0 there? From like why can we take that away? Equate the two times inside each other.
That's so first of all, talking about a point to x as the bounds of the integral, that was how we stated the theorem when it comes to functions. So it's going to be basically the same when it comes to series and not just sequence. Here specifically, I used 0 in my example because I know that 0 is one of the points in which the series converges. So I can use it. And we could have taken half or minus half.
Yeah, I think you made them so well.
What?
I'm asking from the line, actually, from this line here
Yeah.
to this line here, you get rid of this.
Yeah. So what do we do?
Why are we allowed to do that?
What do we actually do? We put t as x minus t is 0, right? So on one hand, on the left side of the equation, putting x instead of t gives us what is now in light blue, and putting 0 instead of t gives us this fraction, right? And that's 0, so I didn't write it from the first place. And yes, all the same for the right hand of the equation. Okay, another thing I wanted to note, not write it down. We can phrase this theorem about indefinite integrals, saying that the antiderivative of the series is the series of the antiderivatives. We can do it. We don't. You can use it if you want. Maybe near practice will show you, but it's not very important, at least to me here in the lecture. We mentioned near in the practice. It talked last week about the holidays and the classes we're going to miss. So I don't know what Nir exactly told you. Today you don't have practice, or next week, or something like that. What he told me is one of the Infi 2 practices is going to cancel because we are not going to study a full 2 lectures a week. But whatever he told you, it's his own decision. He's a big boy, as already mentioned. He decides for himself. Any other questions about the integrals theorem? Okay, so lastly, what we did say in lecture number 13 about derivatives, I want to rephrase it about series. We didn't mention this theorem in the terms of sequences, so maybe you don't remember every part of it. It's not a problem. I just want to write it down. When it comes to derivative, if the series of the derivatives, which is the sum of f and tag, is uniformly convergent to some function g in the segment I, and the series of the original function fn converges in some xfs in I, x0 in I, we can say that there is a differentiable function s such that the series itself of fn converges to s in all I, not just in one point xfs, but point-wise talking about, yeah.
What calculator uses to calculate values?
Oh, that's a nice question, and we're going to discuss it when we get to the Taylor series, probably 2 weeks, as I mentioned. And you should remember Fourier, engineering, French, bad. Taylor, computer science, British, good. Okay, that's what we do here. If you sometimes it depends on the lecturer. If you do have time, it's not a bad thing to know about Fourier series. It's a very, 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 very basic concept in mathematics, but it is not in your limited time, in your limited schedule, and what you study or not study through your first degree. Probably You can leave it to the engineers. Such as an in all I, moreover, that's just a point, and S tag is G. As I mentioned last week, it's going somehow backward. If we know something about the derivatives, we can know something about the function themselves. Now here it is phrased in the terms of series and not of sequences. Technically speaking, as far as mathematical lines are technical, speaking, we can write something like that. The series of derivatives is the derivative of S, which can be written as the sum of the derivatives, let's add x as the variable, is the derivative of the series, which is S. And I call that derivative element by element. Written as and can be called derivative element by element. No, derivative is the noun. I want to write it to the derivation. How do you say it in no the I always go to it because, as I told you, probably maybe you know that when you study English in the Israeli school system, it is all about grammar, again and again and again. Not about vocabulary, not about, I don't know, whatever it should be about. It was about Hebrew, yeah. First of all, as a conservative, if something works, you don't just fix it. But secondly, I think that it probably shouldn't be the same for every language. I mean, different languages have different structures. And it's easier to learn one language. When you study Arabic in the Israeli system, school system, you study as well. You talk about only grammar, and this is the verbs, and this is the adjectives. But Hebrew, it's your mother tongue, you don't say it in English, you talk it all the time. So you have the vocabulary. English, everyone uses the internet, everyone listens to songs, not as such as in Hebrew, but they do have vocabulary. When you study Arabic in the Israeli high school system, you don't have the vocabulary because you don't use Arabic in songs or internet or whatever. So you have only grammar. I mean, it's been, I don't know, 13, 14 years. Then I finished high school. I can talk about the different structures of verbs in Arabic, whatever. I still know it. When it comes to vocabulary, one can see a few sentences, probably half of the words I will not understand, which is probably stupid. And we call blah, 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 blah. Okay. We have another minute. No talking unnecessary stuff. I want to mention you a nice little example. It's called the Weierstrass. As I remember, we can Weierstrass function. Look for it, Wikipedia or something. We can, using our knowledge about series of functions, we can build an example for a function that is continuous everywhere, but is nowhere differentiable. Now we know that not every differential. We know that not every continuous function is differentiable. Our main example is the absolute value. It has its own spitz down there. We don't have a tangent line. It's not differentiable, etc., etc. But yet again, intuitively speaking, from Infi1, we'll be finished. I want to say quickly, it's about specific points along the function. The function absolute value is always differentiable, except this one point of the spitz. What do we say here? That differentiability is a whole different class of function. A function can be continuous everywhere, but differentiable nowhere. And what is most interesting from our basic point of view here, is the graph of such function. How the hell such a function looks? What every point of it's a spitz, like in the absolute value. So we will all be finished. The time and the students. I invite you to look for it in Google. Look for YouTube for a Weierstrass function animation, preferably with psychedelic music. Look at the graph. Look at the graph. It's what is called fractal. Yes, it's one of the but it's one. It's not on the syllabus. Won't be appearing in the final exam, but it's a nice example to look at. And right now, we didn't have the ability to say something like that. If you want.